Hey guys, so in this video what we're going to do is we're going to derive Kepler's third law. So Kepler's third law says that t squared is directly proportional to r cubed. So it means that the time period squared is directly proportional to the radius of the orbit cubed. Okay, so for example, what Kepler did was he observed all the planets in our solar system, and he saw for our sun, when we look at the Earth, when we look at Jupiter, what he saw was that the time period squared, the time it takes that Earth to orbit the sun, the time period squared is directly proportional to whatever the radius is, its orbital distance away is cubed. So what we can say is that t squared over r cubed always equals to some type of constant, right? Because that's what directly proportional means. Directly proportional, what it's saying is t squared is equal to some constant times by r cubed. So t squared divided by r cubed equals a constant. So if I knew what the orbital period of the Earth was, and I knew what the r was, the distance between the center of the Earth and the center of the sun, and let's say I knew what r was, the distance between the center of the sun and the center of Jupiter, I can then use this relationship to find out what the orbital period of Jupiter would be. So what is orbital period? So orbital period tells us the time it takes for the planet to completely orbit the sun. Okay, so if I'm looking at time for one full orbit, I know the speed is always equal to distance divided by time. So the speed is equal to the distance it goes through. We're going to model it like a circle. So the circumference of a circle is always 2 pi r, 2 pi times the radius, okay? Because it's a circle, and that's the circumference of a circle, the total distance that it would orbit around. Divided by the time, and because we're not going to use little t, we're going to use a capital T, because capital T always represents the time for one full wave or one full oscillation. So because it's one full circle, we're going to use our capital T. So that's how we can write what the speed of that orbit is, the linear speed. So the linear speed of that orbit is going to be equal to 2 pi times its radius, and again the radius is from the center of the Earth to the center of the sun, over the time for it to complete one orbit. Okay, so we know if I have the Earth orbiting the sun, we know there's going to be some gravitational force of attraction between the two bodies. And then we can go to our gravitational fields topic. So to figure out what that gravitational force of attraction is, we know it's equal to the universal gravitational constant, mass of body 1 times the mass of body 2, divided by the distance between them squared. So what the force is pulling these two objects together, because they both have mass, and anything with mass has that force of gravity, okay? We know that it's traveling in a circular motion. So things traveling in a circular motion, we then use our circular motion for force. So F equals mass times acceleration. Resultant force is mass times acceleration. But for circular motion, we know that we can write acceleration as v squared over r, or I can write it as mw squared times by r. So remember, v again is my linear speed. R is the distance between the center of the sun and the center of the Earth. But if I wanted to use this equation for W, W stands for our angular speed or angular velocity. And what that is the total angle it goes through over time. So if I was to look at the angular speed, the total angle it goes through is going to be 2 pi, one full circle, 360 degrees. But it has to be measured in radons, which is why we use 2 pi, divided by the time for one full circle, t. Sometimes you then see W as the angular speed written as 2 pi f, because 1 over time is the frequency. Okay. But because, again, we're trying to prove Kepler's third law, that the period squared is proportional to the radius of the orbit cubed, or the distance between the two bodies cubed, I want to then see how can I relate these two equations when I've just figured out that I can get time period into my equation from the speed. Okay. So because I want to use a linear speed equation, I'm going to end up using the linear speed equation and not the angular speed equation. So now I'm going to equate my two forces. So I have now is G, mass of body 1, mass of body 2, over the distance between them squared, is equal to mass of body 1 times the speed squared over by the distance between them. Okay? So for this one, force for circular motion, we're trying to say for circular motion, that mass there is going to be the mass of the smaller body, the mass that's actually doing the circular motion. So what we're cancelling out both times is the mass of the Earth. So I'm cancelling out the mass of the Earth, and what I get left with then is just left with the mass of the sun in this situation, okay? The mass of the thing that all of the objects are orbiting. So what I can do now is I can simplify this, because I want to insert this equation in. I want to see what V equals. So I'm going to rearrange this just to get v squared. So I'm going to multiply both sides by r. I have g times by the mass of the sun divided by the radius is equal to v squared. So again, we multiply both sides by r. Now I want to substitute in what v squared is. So over here, I know what v is. So I want to write what v squared is. It's going to be 4 pi squared r squared over t squared. So that's going to write now instead of v squared. So instead of v squared, I can write that as 4 pi squared r squared over t squared. So again, I want to prove that t squared is proportional to r cubed. So I'm going to have t squared on one side and r on the other side. So what I'm going to do now is I'm going to multiply both sides by t squared and multiply both sides by r. Okay, so what I've got now is that my g times by my mass of the sun times by my t squared is equal to 4 pi squared r cubed. Again, what I did was I multiplied both sides by t squared and both sides by r. So hopefully now we can see g is a universal gravitational constant. For this system of bodies, the mass of the sun is going to be a constant. So that 4 pi squared is a constant. So what I've just proved is that they are directly proportional. So again, just to show you what our final answer here is that t squared is going to equal 4 pi squared divided by g times the mass of the sun times by r cubed. So what I've just shown is that my t squared is proportional to my r cubed because this is a constant. Okay, so it's a constant for the set of objects orbiting the sun. So let's say there was another exam question where maybe instead of these objects orbiting the sun, maybe we're going to look at the moons of Jupiter. So let's say we have the moon of Jupiter, the planet of Jupiter. And what we're looking at is we're looking at all the moons orbiting Jupiter. So some of the moons of Jupiter might be Io, might be Callisto, might be Europa. So we have all these different moons of Jupiter. And again, this time, the capital M, this big M here, the mass, would be the mass of Jupiter. And we're going to say that the time period squared for any of those moons around Jupiter is going to be proportional to the distance between the moon and Jupiter cubed. Okay, so again, it can work for any system that is orbiting one common body. Okay, so then the constant will change each time for different systems, but for a set system, all the planets orbiting the sun, it's a fixed constant because we use the mass of the sun. For the system of all the moons orbiting Jupiter, it'll be a fixed constant because we use the mass of Jupiter to show that the time period squared for each moon is proportional to the distance between that moon and Jupiter cubed. Maybe we look at a different planetary system beyond our solar system, so a different star with planets orbiting. Again, all the time periods squared of those planets orbiting that star will be proportional to the radius cubed, the distance they are away from that star, and the constant will just use the mass of that star that those exoplanets are orbiting. So I hope that was helpful. So click below to sign up to our lessons.